so. You can keep them. You don't actually like need them anymore. This is one of those days like, are we in college? Are we in elementary? Oh my gosh. All right, let's shift. I know. Let's shift back now to lecture. I see that we can keep y'all entertained though with a couple balloons pretty easily, so that's good. All right, so I appreciate your patience in doing things out of order. So this chapter is all about kind of the air and sea, and of course how the air and the sea currents are interconnected. And so that's, our first kind of introduction. So our overview of the chapter is our atmosphere and ocean are interdependent, so they're connected with one another. Right, we've already seen some of that. Okay, we know that the water evaporates and goes into the air, but then how do those air currents move that water around? And so we'll look at that. And we'll talk about, of course, why we have seasons, look at the three major wind belts. So we've already had some fun with the Coriolis effect. And so we'll look at this, again, kind of related to energy. And look at more stuff. So let's see. So let's just get into it. So it talks about Earth seasons. And so we have a slightly elliptical orbit. So that means, right, it's not a perfect circle. It's a little bit of an oval. But this is not what causes our seasons, though. And so what causes our seasons? So the Earth's tilt. So our tilt of the Earth, that is what actually causes the seasons. And I'm sure we already have a good idea of how this works. And of course, so looking at the Earth's tilt, and we'll look at summer, since that's where we are. And of course, we all know, right, we're pointed kind of more towards facing the sun right now with the tilt. So we're experiencing summer in the northern hemisphere, and of course, right, it's winter in the southern hemisphere since they're pointed away. And so once we get at the autumnal equinox, so now it's more evenly distributed, so we get more even amounts of sunlight on the north and southern hemisphere. And of course, going back now in the winter solstice, so we would be experiencing now the cold months as we're pointed away from the sun, so tilted away. And of course, now that would be summer for the southern hemisphere. And then we go back to our middle over here, again, kind of more even warming now. So now that's going to be spring or fall, depending which way you're going. Excellent. So that's what contributes. So fun fact, right, the tilt of the Earth is 23.5 degrees. That may be important. I haven't decided what's going to be in our next exam. Oh, I will. Oh, I should talk about the exam briefly. I totally forgot. So I at least want to talk about the grade. So I just want to say, so our average was a 74 on the midterm, which honestly I was hoping for a higher average with the way I'd written it. I think some people might have just rushed through, but we'll get those back. Overall, I'm not too concerned though, so basically, right, nobody dropped the class or anything is also what I'm saying. So your grade is heavily padded with your organism journal and your labs. So I won't do any like adjusting until the end of like curving. So my goal, right, is everyone to pass. So I'm thinking like A to C range. And so roughly, so quick statistics lesson too. So everyone should take stats, by the way. But right, our average was a 74, but what we also need to know was that we had a standard deviation of 13. So that's kind of large. So that means usually the way people do it is you center your average right around a C. And so it's 73 plus 13. So that would be 87 would be roughly like your B. Then 100 is your A. And of course, right, you can adjust. So that's how people adjust your curves, is what do you truly want your C to be. So I would probably boost this more to like a B. Average is what I would go for in this class, and then center the grades accordingly. But again, I won't do any adjusting until your final grade. So it's just noted in your final grade. So again, I'm expecting to give out, right, maybe A's to C's at worst. And that could obviously change if everybody gets hundreds on all their exams from now on, then, then everybody gets A's. So that's kind of how that works. I just wanted to say that, so don't drop the class or anything. And yeah, I'll hand those back whenever we have some downtime, so probably during lab. I got a ton of papers for y'all. All right, back to this. Sorry, ADD, wanted to say that. And so, of course, these are just our seasons. So you probably at least want to know, like for an exam, that your summer solstice is when it's overhead of the Tropic of Cancer, right, the northern hemisphere. And then versus the winter solstice. So probably, again, just trying to identify broad terms that we might want to know, picking out, since there's a lot of information in there. And so winter solstice is when it's overhead at the Tropic of Capricorn. Of course, that's on the south. And let's see, I think we have a better chart later of the tropics, so we'll look at kind of our zones. So of course, around the equator is the tropics, 23.5 degrees north and south. And so we should note, so I probably won't make you remember the degrees, but we have the Arctic Circle and the Antarctic Circle. And what's important about that extreme degree of either north or south latitude? What happens there? So it is cold. So what are other consequences of it being on those poles? So both are very cold. Kind of says. So yeah, I was going for the length of day and night. So sometimes you have complete darkness, right, for days at a time, and then the opposite. Then you have complete light for days at a time.
Is it because of how the Earth rotates that it's just like the sun doesn't reach that part of the Earth, and so?
Yeah, well, because of the tilt. So in the summer, right, they're going to have the extreme of like all days, right? So if we look at the tilt, so back to this diagram where the Earth is, so then it's rotating, right? And we could take this Earth, right? You tilt it, and so now it's rotating. But look, the North Pole is always pointing right towards the sun. So even though it's rotating for the day, this one, because of our tilt, is still getting sunlight. And then, of course, right, the opposite effect. So then, if we're now over here, where it's pointing at the Tropic of Capricorn, now this is always pointing away from the sun. So even though the Earth is rotating for our day,
so the Earth's not like going in different directions. It's just always spinning in one.
Yeah, so it's always on this axis. So this axis may wobble slightly, but that's not going to cause that much variation. So right, so it's going like this and then rotating around the sun, right? So now it's back over here where it's daylight all the time. Now it's right spring. So it get right, and you just have to look at kind of the variation, the day, night, and then back over this, right, this where it's darkness all the time. So winter.
My buddy was stationed up there, and
Oh, I
because
can
of the,
imagine.
your circadian rhythm or whatever, where you couldn't, your body's like, it's noon, but it's 2 in the morning.
Yeah. Yeah, like I can't imagine, like even for me when I lived in Washington briefly, like I thought that was bad with like, nighttime at 10 p.m., 10:30, but like if
Yeah,
you're,
well, like in the winter when it was dark all the time, he was from the Bay Area where it's sunny most of the
oh
year.
no.
So he had like the depression from like the vitamin D, not getting as much, so there's a lot of crazy stuff that happens when you go to like those extremes.
Yeah, does he use like, or did he use light therapy?
So I think he just took a bunch of, the military never gives you like the stuff that works. So they probably just gave him like the, like 20,000 units of like vitamin D in a pill or something.
I mean,
Gargle salt water.
but yeah, I mean, these are extreme, these are concerns, and right, so you can see that if you move northern, even here in Oregon, we have pretty long or extreme days and nights in some senses, but yeah. I mean, I'm sure there's all stories of like in Alaska too, right? It's like light all night and they're partying at the bars or whatever.
Yeah, spent a time in Norway, and was there for summer solstice, and it's like, it's sort of twilight. Things maybe might be dark for like an hour and a half, 2 hours.
Wow.
And it's like dusk again.
That's wild. Yeah, so it's pretty wild. Just all that from the tilt of our Earth. So yeah, at the extremes, so like you were saying, extreme conditions, either sunlight all the time or nighttime. So that's pretty cool. All right, so now we're looking at, so now there's a lot of different factors when we talk about how much sun is hitting the Earth. And then also, what was this factor? Does anybody know what albedo is? Yeah.
This one, if the light reflects, the radiation reflects, like as an ice, it reflects off of the ice.
Perfect. So this is a good effect, and of course, right, again, when we're trying to figure out, well, how much light is actually hitting the Earth and then staying there. So just like she was saying, the albedo effect is how much light is generally reflected from ice or snow. So of course, even at those polar extremes, even if they're getting a lot of light, a lot of that is also getting reflected back. So that's interesting. And then,
Soil kind of absorbs it.
right, yeah, so darker areas would absorb it. And so that's all factors for figuring out how much exact radiation you're getting. And yeah, so the average for the Earth is about 30%. And then, of course, it also depends at your radiation. So looking, and of course, we're kind of seeing that with the globe. But if we are looking at our lower latitudes, so right, we're going to have concentrated solar radiation. So just imagine if we took a flashlight to our globe, and then it's, of course, pointing at the equator. There's also a thinner section of atmosphere that it's going through. So again, our equators are hot. And then for flashlight B here, so at our higher or more extreme latitudes, now that sun, and so we can look at the circle there. So you're looking at that kind of circle of concentration. So that's literally, right, your area is more diffuse. So that just means that the sunlight is weaker, and so, right, it's less. And then, of course, you mentioned the albedo as well. So all that is playing into those higher altitudes and why it is cold. So remember, lots of different factors, though, that affect the daily weather.
Vitamin D, I have a friend who works in that department, that's her job, and she said the angle of the sun matters, whether we're absorbing the vitamin D. And in our area, pretty much nobody gets enough vitamin D.
Yeah, I mean, that goes back to the, right, looking at the flashlight. So we're up here, right, with those higher latitudes. So yeah, we're not getting the direct sunlight. And so, of course, if that's being diffused, then yeah, maybe I mean, people in general, I think it's like 50% of the population is vitamin D deficient. And a lot of that is we don't get out in the sun.
A lot of it's surface area. Like, you got enough people, if you're out in the sun, still pretty clothed. Like, even in the northern latitudes, you know, especially northern hemisphere, northern Europe, a lot of people would go out and they actually, it'll be kind of chilly outside, but the sun's out. They still go out look naked or semi-naked to try to get the surface area.
I mean, some people say there's benefits to like naked suntanning for that reason. Like,
Surface area.
yeah, it's all just trying to get all the vitamin D. Like, I won't ask about what goes on in Ashland then. Well, now I know.
You cannot unsee some things.
So this is, again, just like a general guideline, again, based upon your latitudes. Of course, looking closer to the equator, we expect to have a lot of absorbed radiation. So looking at absorbed versus reflected of the solar energy. And, and so this is just, again, a general guideline for what you see. All right, so now we'll look at, well, how does the ocean kind of play into this? And so in our higher latitudes, we have more heat loss than gain. So again, we mentioned that ice is really reflective. And of course, we also have just a low solar ray incidence. So again, that light is diffuse, not as direct. And versus our low latitudes, so now looking at our tropics. So here's our Tropic of Cancer, Tropic of Capricorn, and then our equator. So all that zone, right? So now all that is getting direct heat. And so in our low latitudes, more heat is gained than loss. And so now, right, this kind of brings us back to the question, well, why do the oceans not like boil, or how is this heat, how does it move around? And so we're kind of teasing currents. And so this is just like a reminder about our atmosphere and what gases are in there. And so, right, we're mainly nitrogen. And why are we mainly nitrogen? What's the property about nitrogen that makes it so abundant? So it's inert, relatively speaking. So inert just means that it doesn't react with a lot of compounds. And so actually, when they do like sensitive chemistry, they usually use like nitrogen, and you fill a glove box in a completely nitrogen atmosphere, of course, getting rid of that oxygen. And so oxygen has the trick of that it does react with a lot of things. So I'll just put, because there's lots of iron oxides. So, right, iron oxides are the big example, but you can have a ton of other metal oxides. So oxygen is just more reactive, right? We see it reacting, making rust on a daily basis. So oxygen is obviously reactive, and nitrogen is not, so that gives us a large composition since it's less that it can bond with. And then, you know, another reminder, carbon dioxide is relatively small, so only about 0.04%, so not that much of our atmosphere. And so let's just put, right, a reminder that probably 0.02% CO2 was considered low historically for the Earth. So if you remember back to other chapters where they said they saw where like the plants weren't growing because there wasn't a lot of CO2. And then, of course, trace gases, you have some methane in there. All right, so let's look at our atmosphere. So if we look, so we have our troposphere. So this is the lower level, so our lowest layer of our atmosphere. So this is where all the weather occurs all around here. And so, of course, if you compare that with our little graph here, and let's zoom in. So our stratosphere, this is where airplanes are going to be going, and even not too high, right? So they still tend to be under like 10 miles, so pretty low, just above the weather, though, for good flying conditions. And you also can't be too high, as the air does get increasingly thinner. And then we have our high altitude ozone layer. So our ozone layer both keeps us protected from the harmful radiation, and then also gives us a nice blanket to keep us warm so that we keep our atmosphere. And so in general, so in our troposphere, so just starting in our troposphere, so atmospheric temperature decreases with altitude. So again, this is in the troposphere, so what we see kind of in our weather. And then as you go higher, so now in the stratosphere, now your temperature starts increasing, again, with increasing altitude, probably some effects of more direct radiation at that point. Then you go into your upper atmosphere. And so again, since we're just focusing on our troposphere then, we'll think about things as a convection cell. So we'll just start with our simple convection cell. And I'm sure you guys saw that with our last lab. So so your warm, either air or liquid is going to rise. And so this creates, once you have rising air, this usually creates some sort of low pressure as it goes up. And then this cold air coming back down, rushing, creates more high pressure. So all that air kind of rushing down. Yeah.
Something that helps me to understand that, as I was reading, is that the low pressure, when the air is hot, that the molecules are busier and more spread out, and so there's not as much pressure as when it's cold and they're closer together and less active. The pressure is one of those air molecules, right, that are closer together and
Yeah, so you have,
cold.
yeah, you physically have a lot of them, so that creates a lot of pressure. But then you do have the temperatures, because what's kind of funny, and maybe you're getting at this, is of course at the poles, right, you have a lot of high pressure. And so what does that high pressure bring, though, like weather-wise? What kind of condition?
Rain and thunder and stuff like that, right?
Other way?
Or is it the opposite? Okay, I'm thinking of barometric pressures. So,
Yeah, so kind of dry, but also clear, right? So yeah, kind of what you were saying. So if it's high pressure, usually it's just like the air molecules, and there's usually less water molecules to kind of in a high pressure system. And then yeah, like you were saying, because there's so many of them, so you have to think about them as a molecular level. So they're all like knocking against each other. So that creates your high pressure. So then they start moving, and you get that high pressure. And again, it's still cold though in the poles, but then you get those clear conditions. There's no rain there. So that's why it's usually dry in the poles, even though it's cold. Let's see. So again, we mentioned our warm air rising. And so, right, it's less dense. So it is still moving fast though, but it's less dense in that there's less molecules, right? So they're kind of further apart, and so not knocking into each other. And then, of course, as they rise, they also leave low pressure behind, and that low pressure is what invites the storms in. So if you have low pressure, then storms would be attracted to that kind of low pressure area. And we'll look at more graphs. And so again, typically warm air is moist. Again, we'll look at that since it evaporates around the tropics, versus our cool air, which is typically dry. So we are looking at atmospheric pressure. And so there's different measurements for it. I think you mentioned barometer or barometric pressure. So that would just be like another unit of atmospheric pressure.
Yeah, I had it backwards. In fishing, you follow the barometric pressure a lot, because it affects where they're at in the water column. And it just, that's how fish decide when they want to eat, is based on,
Oh, I didn't know that. That's cool.
they get lethargic when it's too low, I believe. Yeah, when it's too low, they don't like to eat. When the pressure's low, when it's high, that's when they get active and aggressive.
That's funny. I mean, that kind of makes sense of like high pressures, like better conditions, like clear weather.
But it doesn't mess with their float glands and all that. Their swim bladders aren't as fickle when it's.
Oh, yeah,
So
that's
they get,
interesting.
like, a tummy ache when the pressure's low. When it's high, they're like, it's wild. Like, anglers are obsessed with the barometric pressure.
I did not know that. Yeah, that's pretty cool. Let's see. So there's different ways to measure it. They should have put a picture in here. Or maybe let's look up. So are people like familiar with a manometer? I think some people are. I'm trying to find like an old school one. This is not the best graph that I was hoping for. Here we go. This is what I'm looking for. So this is like the very basic explanation of pressure and how it's calculated. So you have some sort of substance. It could be water or mercury. So mercury is usually a good choice because it's super dense, so it doesn't like flow wildly with the changes in pressure.
Super toxic.
It's actually not that
It is
bad.
probably not in small doses.
Well, it also, so elemental mercury, I think gets a really bad reputation. So obviously you shouldn't like drink it or put it into
Put it in
the.
your hat.
Yeah, but it's like if you just like keep it contained and just use it like this, it's perfectly fine. It's just when
We
you.
used to play, we'd break them and we'd push them around with sticks.
Yeah.
Blobs.
Yeah,
I
that's.
remember like an old dude walked in, he's like, "What are you guys doing? You guys are gonna die." I was like, "No, it's cool.
Yeah.
We're not touching it. We're just poking it."
Even if you touched it, like it would be okay. Like it's a bad rep. But yeah, organic mercury though, super toxic, will kill you. As long as, once it gets organo. Like methyl mercury killed somebody. Like just a tiny drop. Because once it gets that organic, then it can cross your blood-brain barrier and
So
then.
is it just kind of like how asbestos has a really bad rap? You know, there's a lot of different types of asbestos, and there's like 4 or 5 that are actually dangerous, or like over long periods of exposure will make you sick, versus the other, 100 or so that are actually not bad, but there's like a few, says mercury the same way, where there's a couple bad ones, and then there's like the ones that are okay, so they just say, no, it's all bad.
Yeah, I don't know really like why mercury started getting such a bad reputation.
Because that's what they taught us, was like, oh, the Mad Hatter is based on some guy putting mercury in his hat, and then you go,
Yeah, but yeah, because what's funny is I think they were using more like mercury compounds. So like, yeah, they did use mercury-based compounds in like cosmetics, and I don't know if anyone like took mercury. So obviously, if you ingested like mercury, which they may have done back in the day, like they did crazy stuff, right? Like that might make you crazy. But as long as you're just like touching it and not mixing it with stuff like mercury,
Well, yeah, 'cause that was
it's
a big
pretty
thing
safe.
with lead too, like with painters, they used to straighten their paintbrush,
Yeah,
clean it with their mouth, and there was lead in the paint.
yeah.
And so you had a lot of issues with that too, but, sure you don't touch it. Like I said, the dude came running in, yelling at us like, "You're gonna die."
Oh, yeah, that's crazy. Yeah.
We used to break them on purpose so we could do that.
Yeah. Yeah, one time well, it wasn't me that made the mercury spill. One of my grad school colleagues, like, turned on the nitrogen like crazy, and then the mercury came out of our manometer, so it, like, sprayed his fume hood. And that's always a fun time when EH&S shows up and was like, well, you guys are the experts, so you get to do it. So we were the experts, and so we made like a makeshift vacuum essentially, and like sucked up all the little mercury beads into one big mercury glob again. And then with the residuals, because it like literally sprayed everywhere, so then there's like microscopic mercury things everywhere, and then that we had to sacrifice it. And so how you clean it up is you add sulfur to it, and then it makes more toxic waste, but at least that can be swept up and then disposed of.
Does it turn it into a powder, or does it turn into like little rocks, or like what does it do, like the sulfur do to it?
I think it's hard to tell, so let me look up. So mercury sulfide. So it's probably like a little, so we'll make like this sort of thing.
It's like a little dust or.
Yeah. But usually you only do this like when you're cleaning up the residue. So what you want to do is scoop up everything into one big mercury ball.
It's so cool that how they feed and like.
Yeah.
I always thought it was fun.
Yeah, and you should definitely take advantage of their beating property to keep it together, because it's once it gets like aerosolized and spread everywhere that starts getting dangerous, because you just don't want to accidentally ingest anything. But so back to this manometer. So if you look at this picture, right, literally it's measuring all the molecules smacking down on the mercury, and them smacking down on the mercury drives it up this column, since this is a vacuum out tube. So that's how they measure the pressure. And so that's where you get these like weird units too. Like if you notice, right, this one, because it's literally measuring how many millimeters of mercury. So that's why we say atmospheric pressure is 760 millimeters. So this is millimeters of mercury, or 29.92 inches. And there's all different scales. And so, right, this one, 14.7 pounds per square inch is 1 atmosphere as well. So again, just different units is all that is. And so if you have a thin column of air, that means you have a lower surface pressure. And that makes sense, right? Less air there physically, so less physically pounding. And so we mentioned if we have cool and dense air with a lot of molecules, then we'll have higher surface pressure. And then again, versus the moist air rising. So if your air is rising, then there's less of them smacking down. And so this is important. I would maybe expect this to come up on an exam. So air always flows from high to low pressure, right? So same thing with solutions, so high concentration to low concentration. And so this is just our general convection cell, right? Earth's warm surface, then the warm air rises, cools down, and then starts getting dense and sinks back down, creating that high pressure. And then again, the low pressure from your air physically going higher. And so this kind of teases us back into our Coriolis effect. And so the first thing is, we'll just imagine that our Earth is not spinning. And so if our Earth was non-spinning, then it would be really basic like this. So we would just imagine our warm air at the middle, and then it would travel all the way to the pole and make one big circuit. Of course, we know that this isn't the case from studying the wind patterns. And so this now goes into, right, our Coriolis effect. And so it deflects, again, our path depending on our viewer's perspective. And so we kind of looked at that. So we're looking at the Earth's rotation. And so again, same thing with like if you're throwing a ball on a merry-go-round. So you and the other person are spinning, right? You're passing the ball back and forth, back and forth. It looks like you're doing it in a straight line. But to the outside observer, right, it would look like you're rotating the ball and kind of moving it on a curved path. And so, right, our Coriolis effect, and again, it's depending where you're going. So we have, of course, our fastest velocity near the center, near the equator, versus our poles, where we basically have no extra velocity. So, of course, it depends how high. And so, like we were mentioning, it has the greatest effects on objects that move long distance. And that's why we mentioned, right, the two big uses for this would, of course, be like plane courses and missiles. So things that need to travel long distances over the Earth. And again, that would be a traveling above the Earth, so they're moving different relative to the Earth's rotation. And so back to our missile. So now we're trying to bomb New Orleans. But then we'd have to look like we're going in a curved path, because again, your Earth is rotating. So if you actually want to hit New Orleans, you need to compensate and look like you're going to the left or to the right if you're from the northern perspective. So that kind of gets confusing too. So you have to orient yourself whether you're from the bomb, so then it looks like you're going right, and then you're always right if you're orienting yourself from the bomb's direction. So then Galapagos Island, right, again, to hit New Orleans, we have to compensate and now go to the right, at least from the perspective of the bomb, to hit New Orleans. See, do we have a picture? Yes. And so now let's look at what we actually have. So this is our picture of what's actually going on. And so we have kind of three main little circulation cells here. And so our lowest ones are the Haley cells. So that's going to be in this region. And so they go about how we would expect. And so let's look at first the general circulation. And so with these currents, so we're looking, right, the equator is where we have a bunch of evaporation. And then by the time we get to around 30 north or 30 south, that's when it starts losing energy, starts cooling back down. And so what might you expect? And so it tells you also what kind of weather you expect. So if it's cooling back down, right, this is creating high pressure, so we expect kind of more clear weather conditions. So right, this is high pressure here. And then low pressure. So the low pressure regions, you're going to expect a lot of storms at the equator. You want to say something or? Yeah. Oh. Oh, you just looked excited. So I didn't know if you had a story.
So I've been to Ecuador. I was there for like 2 months, and because they're pretty much right on the equator, and it was stormy the entire time I was there.
Yes.
Lots of earthquakes, lots of thunder and lightning.
Oh, we're on the wrong side of the globe. But yeah, exactly. So that's good. And so they mentioned something else with this region. So it's stormy. And how did that affect sailors back in the day?
Sure, lots of them died.
But what did the storms give them, though?
Wind.
Just fresh water.
Yeah, fresh water. So let's look at the wind though. And so now we're looking at these trade winds. And so what do you notice about these winds? And of course, what's probably affecting them?
I'm sure their navigation route.
So navigation routes, so this was, of course, and they were considered trade winds because they're going to be steady. So then let's put, right, navigation. So of course, right, essential for trades. But what do you notice about the curve of that? What is affecting this curve here? Yeah, and what was that called again? Yeah, so this is all from our Coriolis effect as well. So we have, right, our winds kind of turning. So you can see they're turning this direction. And then here, so like you were saying with this low pressure, and you noticed that, you saw that there were no storms, but then there's also very low wind here. I don't know if you noticed that. So, yeah, so
It
no,
wasn't windy, it was just, there was thunder and lightning and, I don't know, it was hard to, it was 18 years ago, but,
yeah,
it stormed a lot.
that's awesome. I mean, that's like exactly what the textbook says, like super stormy, and then the ships would get lost out here potentially since there's not a lot of wind, like you observe, but then they get at least fresh water from the storms, so they might be stuck out here, hopefully not for too long, until they, can get back on, like you mentioned, these trade winds that are actually moving.
Yeah, here's a fun thing I read over the weekend. Talk about sails and stuff. Did you know they discovered that they can put a kite on a cargo ship now? And instead of using fossil fuels.
So we're going back to
Just
sail
say
ship?
we made the full circle. Isn't that funny? Like someone really woke up one day, like, we can put a kite on a ship and thought it was a new idea.
I'm just debating if I want to go on a CO2 fossil fuel rant or not. But yeah, it's basically all about money. So if we can reinvent our sailboats, that's what it's about. You just got to get some angel investor to get on that kite.
It's just silly. Like, we made full circle around the technologies and sailboats are in again.
I mean, that's why history is important. We just keep coming full circle as a society. We never learn. It's okay.
Well, because the idea of sailing is kind of evergreen. It's not really, the classics always last. So we just dress it up and call it something different. Now we're gonna call it kiting or something.
Yeah.
I just can't wait till that happens and two ships just get close enough and they get all tangled up in each other, ruin their week and a half trying to fix that.
Yeah, and then be on like TikTok or something. And everybody will just be watching them
Going
crash.
back to fossil fuels, everyone.
Yeah, that'll be it. All right, so let's look. So we're gonna skip the ferrule cell for a second. And so let's look at the polar cell. So now that's in our extreme zones. And so as we kind of expect from what we mentioned, so our poles, right, they're really cold, but they also have clear conditions. So up here we have our high pressure, again bringing our clear skies, and then our low pressure, so around 60 degrees. You have kind of these polar front areas, so imagine there would be pretty stormy here, so same thing at the bottom at 60 degrees. And then, so what's interesting about the ferrule cell circulation? Oh, what's interesting about the ferrule cell and its circulation and how it kind of fits in? So this might be,
Oh, it reverses.
Yeah, so ultimately it does reverse. And so why that is they describe it as it kind of just falls in between the polar and our Hadley currents. And then it's kind of forced to kind of go along with it. So it kind of looks like it's in reverse, which is interesting. And so, right, we still have high pressure, low pressure. It's just circulating along with the Hadleys. So notice, right, in these 30 degrees north where we have our high pressure kind of from our Hadley current here, we're going to have the same thing except it's going towards the equator. So high pressure and then to low pressure. And then in these higher altitudes, it's relatively, again, warm, kind of with the polar one. So it kind of fits in with the polar current and a Hadley to fit along there in the middle. All right, so that's pretty important. So you probably want to know, again, we have 3 circulation cells. Might quiz you on the name or test you on that, just trying to put big ideas out there. And you guys can help me too, what you think is a big idea with these chapters. And so we kind of looked at that. So again, identifying our high pressure zones. And then versus low pressure. So again, our equator, and then our 60 degrees where we have more storms, relatively speaking. And so, of course, driving this as well as our global belt winds. And so we mentioned the trade winds. Of course, this is just global circulation closest to the surface to generate winds. So again, we're just looking at our lower atmosphere. And so we mentioned those trade winds are super important. So we could go back to this picture, again, looking at our trade winds and the direction they're going. So if you're looking from the orientation of the bottom, looks like they're going left. And then you orient yourself the other way and going right. And then we also have our westerly wind belt. And so let's go back to our picture. So prevailing westerlies from 30 to 60. And same thing on our southern hemisphere, so 30 to 60, your westerlies. And let's see, boundaries. So we mentioned, again, the doldrums at the equator. So that was just the area of low pressure. And then your horse latitudes are going to be between them as well. Bless you. So you have your horse latitudes kind of between these trade winds and your westerly winds. And let's see. And your polar fronts. So this is going to be where you have, again, a lot of storm activity. Usually occurs there. And so let's see. So if we look at this chart, so this is a pretty good summary. So right, again, our equatorial region with our doldrums, so low atmospheric pressure, so not a lot of winds, so kind of light, and a lot of cloudiness. So it mentions, right, breeding grounds for hurricanes, which we'll talk about hurricanes. I'm sure everyone has good stories. Then we have trade winds. So again, just looking, this is north or south, and so pretty close to the equator. So again, those were strong, steady. Then once we get to those horse latitudes, so that's going to be high pressure, so kind of more clear weather again at the horse latitudes. And we can see that here, right? Again, high pressure horse latitudes, clear conditions. And then we have our westerlies again. So just looking back, correlating And so again, we have, those usually bring storms, especially across the US. Then our polar front, so this is, again, where we mentioned there's a polar storm, so generally cloudy, stormy. So now we're back to here, and look at the cloud that correlates with it. And then we have our easterly belt, so now we're pretty extreme, right? So now our polar easterlies, again, from our high pressure going to low pressure at the poles. And so those are going to be those cold, dry winds. So again, that's why it's usually considered like cold, clear, and dry at the poles, which almost seems counterintuitive. And then our high pressure just at the poles. And that's where cold desert term crops up. And so this is just a more kind of detailed picture, you know, putting everything more together and then looking at it with our continents. And so again, you can just tell areas of low pressure, so you might expect there to be more storms in our low pressure regions, and then high pressure should be clear. And it's all relatively speaking, right? High versus low, and you'll hear the weatherman talk about it, and it's all relative, what's going to be happening. So high pressure usually means clear weather, and then if you have low pressure, then that's where they say, oh, we have a low pressure system coming in, right? So if you're low pressure, that kind of invites, right, something to come in from a high pressure system. Questions, comments? Ready to be weatherman now? And of course, right, again, we mentioned all these systems are complex. Since we have, of course, our tilt, our seasons, we have to take into account, right, heat capacity. So don't forget that. So, right, our heat capacity. So water has our high heat capacity, like we mentioned our last chapters, versus the rock. So that's obviously lower heat capacity. And so weather, of course, is conditions of atmosphere at a particular time and place. And climate is just long-term average of weather. And I guess I have to make some comment. I have issues that your book is like, oh, climate change is totally settled. Yeah, so we don't know anything, really, whether it's a cause of human emissions or not. I don't want to get too far into the rabbit hole of it. I mean, there's just so many theories, too. Also, were you guys aware that, like, in the 70s, they were predicting an ice age? So some people know. Let's see if I can find the video while we maybe go on. It's kind of an aside, but like climate. Oh, cyclonic. Yeah. And climate, I think we even have to better define, like, what is long-term average weather. Let's see. Sorry, let me find this video. Okay, let's hope this is the correct one.
At least 8 times in the past million years, it has advanced and retreated with clockwork regularity. If we are unprepared for the next advance, the result could be hunger and death on a scale unprecedented in all of history. What scientists are telling us now is that the threat of an ice age is not as remote as they once thought. During the lifetime of our grandchildren, Arctic cold and perpetual snow could turn most of the inhabitable portions of our planet into a polar desert.
In 1977, the worst winter in a century struck the United States. Arctic cold gripped the Midwest for weeks on end. Great blizzards paralyzed cities of the Northeast. One desperate night in Buffalo, 8 people froze to death in marooned cars. Pat Bushnell was on the road that night.
Traffic just absolutely stopped. I was afraid of being stuck in the car all night long with the cold and the wind, running out of gas, and then what? I think that if we had to go through a real bad winter, just like we just went through, I think we'd have to think about moving someplace else.
Move where? The brutal Buffalo winter might become common all over the United States. Climate experts believe the next ice age is on its way. According to recent evidence, it could come sooner than anyone had expected.
All right, so that's pretty good. But, I mean, I think even us as humans are trying to figure out what does climate even mean. So, right, just in the 1970s, so we totally thought there was going to be an ice age.
Well, then we went to global warming.
Yeah, so now we're...
And now we chose the most androgynous and like basic term climate, and now it's just like whatever fits, whatever storm is happening. You know, we had somebody light the trees on fire, and it was like, oh, climate change. You know,
Yeah.
someone literally got caught lighting it on fire. So I don't know. I think it's silly that we went from ice age to the heat is warming up to now we just chose a word that just catches everything, so they can't be wrong.
Yeah, that's why I couldn't resist talking about it, because it's so politicized. And honestly, like, I think people just want, right, it's all about control and your dinero.
Be afraid, be very, very afraid.
Yeah, and it's like, if you really care about climate change, like, just go plant a garden and call it a day, and like plant some trees. Like, that'll do a much world of difference than, and I'll be the first one to tell you it's a load of bull, because that's how my PhD research was funded. And I put, yeah, CO2 levels have been increasing since the Industrial Revolution. Why? Just so you can get funding, because that's how you get funding. Because again, no one's gonna pay me to study bonding, which is really what I am interested in chemistry, but that doesn't sell you a nice picture of, oh, I care about silicon germanium bonds. Literally nobody else does. But yeah, climate, you can sell it and, whoa, we're gonna die. And like, not to go too much down the rabbit hole, but like, I've heard certain geology professors even argue, like, maybe it's a good thing if we are doing this, because we are overdue for an ice age. So that's what people are concerned about, is like, we should have had an ice age, you know, judging by whatever cycles of the earth. What if we are warming it, but that's keeping us from having an ice age? And like, who knows, right? Nobody knows anything really. And so let's just look at another graph. And again, like, who really knows if these temperatures are accurate? And like, so here we are, you know, somewhere around here. And so this is, again, just what they assume the average global surface temperature was. Again, who knows if this is accurate, but even from our own, you know, scientific evidence from the Earth, like, we've been hotter. So, you know, who knows? Who knows what's going on? I know people like to talk about how quickly it's rising, but, you know, even then, how accurate is our record? Like, this kind of jumps.
We've been a blink of an eye compared to the world's
Yeah.
history. So how do we really know, like, what, I don't know, it just seems weird that we could make such a conclusion about
Yeah.
such a long period of history versus our little drop in the bucket.
Yeah.
And that drop in the bucket is when we actually started calculating like temperatures, right?
Yeah, well,
Everything compared to how long we've been around.
Yeah, because I think there's been a lot in the news of like, oh, these are the warmest temperatures ever recorded, but it wasn't it only like the 1940s that we were like accurately recording?
I think it was like 1940s or something.
Yeah.
Started trying in the early 1900s.
Yeah, and like that's always a good question too for science, is like how can we, you know, reliably keep track of records too if the temperature scale changes, like small things like that. Like even if you research like the human body temperature and how that was determined, it's like, yeah, there's been small fluctuations all throughout just because of temperature, and as we get further on in time, you know, we at least make it more accurate to our standards, that we can have a standard. But yeah, that doesn't, we can't go back and fix the past now and get accurate records. So it's, I think we as people need to define kind of what climate is, because long-term average, like, what is that? Because, yeah, we are nothing compared to if we believe the Earth is 6 billion years old or 4.5 billion, whatever billion, yeah, we're like,
Well, and even if we're basing information and evidence based on like people from like 400, 500 years ago, how do we know how accurate they were actually being?
we have no idea. Like, yeah, exactly.
Like, I hope in like, 400 years from now, someone's like, yeah, maybe they weren't right. Maybe there was, they weren't perfectly accurate on what they were doing. That way, they're not just assuming that the person before them was correct. And it's a bad way to build anything.
Yeah.
But it works, it makes money and scares people, so it's a good racket.
Yeah, I agree with you.
Maybe I'll get into the climate change business.
You should. You can totally get so much money. Carbon capture, but no one talks about a tree. That's a great carbon capture device, but that's not profitable, right? Planting trees, having people garden. That's not scary, yeah.
My wife and daughter do it as a hobby,
That's awesome.
so
Yeah.
it's just something they do because they enjoy it. But I don't think they ever intertwined it with climate change because it's just, like you said, so polarized now that if you mention it on either side, someone's gonna get angry at you.
Yeah. And it's like instead of talking about anything, we should work towards sustainability. And you should never demonize, any form of energy. You got to figure out and we'll go into this later in this chapter. It's we'll talk about wind energy, but there are only so many places where it blows, effectively.
Where there's no wind.
Vast potential for solar energy, and there's
Well,
all this research that's been done.
I have issues with solar.
Really?
Well, what do you need for solar? Let's talk about. Well, you need sunlight, but what else do you need? So you need lithium, but you need other stuff. You need a lot of minerals, right?
Yeah, you need battery backups, you need battery
Well,
backups, and you need.
we're not even there. I'm just talking about solar panels. Literally what's in the solar panels. A ton of metals, precious metals. So where do you get those metals from? Who mines them? Yeah, that's where
Fossil
the
fuels.
cobalt mines. So that's where you exploit African labor and child labor to mine all these precious metals to make your solar panels. The other issue with solar panels is they're only estimated to have a lifespan of 20 to 25 years. So after you have that solar panel, what do you do with it? How do you recycle it?
They don't.
Unfortunately, that's what usually happens.
Well, it's just like the electric cars. Yeah, they're fine and dandy until you realize that when a battery goes bad, what happens to it, or all the stuff that goes into building one of those batteries, there really is no net positive.
Yeah.
It is actually, there's more drawbacks to an electric car than there are.
Yeah, and there's still and then where does you're not even talking about the battery, where does the electricity that you put in the car came from originally?
Hopefully a solar panel.
Yeah, hopefully a solar panel, or else you're essentially, so from thermodynamics, right, you burn fossil fuel to then put it in electricity where you start losing heat and efficiency, whereas you could just burn the combustion in the car. So I have issues with that, but yeah. But I'm not saying that, solar can't be used to supplement. It's just we also need to be sustainable with where we mine our stuff and then what we do with the panels afterward, because we're not very good with life cycles.
Nothing that can be done, they're just trapped.
Well, that's how people treat them, because it's just not profitable to recycle,
Well,
unfortunately.
yeah, it probably costs thousands of dollars to get rid of them the correct way.
Yeah, and so honestly, a lot of how recycling happens is
We don't really recycle.
either we don't recycle or we sell our trash to China and then they go burn it to get everything out, which of course is great for the environment, right? So we care so much about climate change. We're gonna burn all the trash, release all that plastics and crap into the atmosphere, and then all the metals that were in your computers or solar panel, whatever they're burning. So whatever they don't collect up ends up in your water stream and starts poisoning everything. So yeah, that's usually how
But when
recycling
I was in Afghanistan,
goes.
the base I was on, right behind where I was sleeping, 50 yards, there was a tire burning plant.
Yeah.
And they thought that eventually it was gonna go out, but tires don't disappear, they just stay on fire.
I mean, all that is, so what are tires made out of?
Oil.
Yeah, oil. So they're refined oil, so that rubber's just gonna.
Yeah, just
it's gonna
It
burn.
smells bad, it hurts your head, and it's super interesting.
Yeah.
Maybe we should burn tires for fuel.
You know, honestly, I was just gonna mention, like, there's this, it's kind of just a term, I think, but it's like biomass. But it's just, I mean, it's basically what we used to just say, like wood burning. So, like, you used to burn wood. So it's the same sort of thing, just like burning stuff, right, to fuel. So it's just kind of a new, sexier, modern term that people use, biomass, and maybe you can recycle and figure out how to efficiently use it and maybe burn it better, but yeah.
Yeah, that's how they fueled the DeLorean. They were burning trash.
I didn't. Oh yeah, now I think I kind of,
From Back to the Future.
I didn't catch on with how efficient the DeLorean was. Yeah, anyways, we kind of went on a tangent.
I'm sorry.
I mean, it's hard not to talk about everything, though, with this book. That's, because, yeah, you know, they talk about climate, but now it's like, I don't even know if we can define what climate is.
You know what's funny? Maybe we'll all end up wearing kites as backpacks. That's how
Isn't there, like, that used to be an exercise where you, like, attach that kite to you. Yeah.
resistance training.
Yeah. Or, yeah, we'll all be wearing, like, yeah, those jumper suits. All right, so back to cyclonic flow. And so all this, so this goes back to kind of the hurricane rotation that I had mentioned earlier.
Isn't this what you were saying doesn't happen though because of the toilets?
Yeah, so the toilets don't show this, but a hurricane
Oh.
would, yeah. The people always say, oh, it's the Coriolis effect for the toilet, but it's not. Yeah, it's just however your drain's designed.
Okay.
Yeah, because that's too small of a time scale, because it's too fast.
That they have at, so when I was in Ecuador, if you go to Quito, which is the actual center of the earth, there's like a little pen there and that where like, and they had two sinks that you pour water in, and it wasn't like, well, I don't know, it was a long time ago, maybe it was rigged for that, but when you
It
poured
might have been rigged, honestly.
I don't know, I was young.
Yeah, I would have to, because, yeah, sometimes they do that. It's like, oh, we have one on one side, one on the other, but it wouldn't be enough of an effect.
I didn't know now, knowing I wouldn't think so, but I feel like this is what they were trying to explain.
Yeah, they could have been. And, like, some people do, like, erroneously
Or it's
attribute it.
just a tourist trap.
Yeah. So for your cyclonic flow, again, we mentioned counterclockwise around your low, which would be, so your area of low pressure is how your hurricane starts. So, right, a bunch of low pressure, so we mentioned in the equator, it's caused by evaporation, and then you kind of get storm clouds, and then you get that cyclonic movement, since everything's trying to be in the center, so all the air is trying to go to the center, but then your Earth is moving, so it's like shifting, so that's what gives it, again, that counterclockwise rotation in our northern hemisphere, and then clockwise in our southern. And so again, this is more just weather patterns, at least just, you know, appreciate it. For something like this, if I were to put it on an exam, you know, I'd probably just say, like, identify like areas of high pressure to low pressure, like where you expect storms, something like that. So you just want to be able to kind of read this.
How would you read that though for pressure-wise?
So-
The numbers?
Yeah, so then you're just kind of comparing, so right, this is 1020, and it looks like, I assume we're in, yeah, millibars, maybe? I would have to look at. I'm not
So is
sure
it
what
like
you-
a topographical map, the closer they are together, the higher the pressure?
Or, yeah, the spacing should indicate,
More pressure,
yeah.
and the wider would be lower pressure?
Yeah, I think so, because you have your high pressure, all that up here with more lines versus your low, and you have this,
Big gaps between the lines.
yeah, and then of course you can read the pressures as well, so 996 versus 1020. And it's a relatively small differences, but of course, this all drives weather patterns. And so we also have effects due to land and sea heating. So if you have a sea breeze, it's from the ocean to the land. And so a sea breeze occurs during the day when your air warmed by the land rises, so it creates kind of this low pressure, and that invites your cool air in from your ocean. And then from your land breeze, so that occurs during the night after your land has cooled, so now your warm air is continuing to rise over your ocean versus your land air going out to the new low pressure area. So again, just high to low pressure, that basic concept. So let's see. So of course, storms, this is just disturbances with strong winds and precipitation. And air masses are large volumes of air with distinct properties. And so of course, land air masses tend to be dry. That just makes sense, right? Land, not a lot of water. Versus marine air, which is going to be moist. And so again, we can just kind of appreciate this. And so of course you can see you have this maritime polar air mass coming in, and then see where your continental polar air mass is generated. And you can see your air kind of flowing from the oceans to our continents here. And of course, right, this kind of airflow tends to generate hurricanes with our tropical, again, air mass. And so fronts, we kind of touched on that in our graph here. Oops. With our polar front, right? So anytime you have a front, that's your boundary between your air masses. And you can have a warm front where warm air moves to a colder area. So there's our warm air, then it's probably going to leave behind some rain. Then it goes to colder air versus a cold front where cold air mass moves to a warmer area. So cold air will come in, maybe to an area of low pressure, so bring that breeze in, probably left behind by the rain. So storms generally develop at fronts then, and we also have what's called our jet streams. So this is just narrow, fast-moving easterly airflow. So it's usually at our middle latitudes, and we can get some unusual weather patterns. And so I mentioned hurricanes, so large rotating masses of low pressure. And so of course, right, strong winds, lots of rain. Has everyone experienced a hurricane? So a lot of people haven't, some have. So yeah, a lot of, and it really depends what does the damage on the hurricanes. So looking at this categorization, so you have, right, tropical depressions. And so these are all just defined by their winds. So winds less than 38 miles per hour. Except what can be the issue with tropical depressions and the damage they can cause?
Rainfall, flood.
Yeah, rainfall, flood. So, you know, every hurricane, of course, is different, but even if it's a tropical depression, sometimes those can just sit in one area, and if they kind of get stuck there, then they'll just dump down. Yeah, so you could still get some devastating effects even from a depression if you just sit there and flood. I know that happened to Houston. I forgot what the name of it was, though. Where just like, was it Allison, Tropical Storm Allison? That was a bad one, so and we can all tell our hurricane stories. So it was weak, it just dumped water. And then tropical storms are just classified as 38 to 74 miles per hour. And now hurricanes are above 74. And then people are probably familiar with this CAT scale category. So again, they're just categorized by wind. And so like category 3 is still pretty devastating. So category 1, they just say minor damage to buildings. Again, this depends on kind of flooding too, but usually not too bad. Category 2, that's where you start to see kind of more damage, some trees blown down. And then category 3 starts getting more extensive. Of course, category 4 and 5, those are going to be more extreme. Category 5 is where you might have roof failures, where your whole roof just comes off.
Trees being thrown into people's windows.
Yeah, trees. And again, it depends how bad. Usually in these areas, right, they do try to build the building stronger and the roofs more secure so they don't fly off. But of course, you know, at some point,
I
they're
don't
just,
know about that. A lot of trailer parks down there.
well,
So, when you're in, so when I was stationed in, Mississippi, a lot of their homes are like only because they're built on stilts.
yeah. Yeah, so yeah, people do build, right?
They actually use their shutters, not just for decoration.
Exactly. So yeah, houses built on stilts there.
I grew up in a lot in rural Florida, and just like everything's up on cinder blocks, at least a foot or two.
That's cool.
At North Carolina, mostly brick homes where I was at. Lumber.
Maybe a lot more change elevation there.
Yeah, so
More central Florida.
I assume
We go sub-sea level.
brick tends to be stronger for hurricanes. Because I notice on the West Coast, they probably use less brick, right? Because
So
it's
we use
not
a lot of
good.
concrete, because concrete can, yeah, that's why a lot of the bridges, there's some cool videos of bridges actually like swinging in the wind and like being flexible.
Yeah,
Just because we have the earthquakes and stuff like that over here more than, I mean, the West Coast, we don't get a lot of hurricanes.
yeah,
We do get earthquakes more, and so our stuff has to be able to have some give and take and some flex when it comes to that, so it's just different needs.
yeah. I mean,
Florida would just get destroyed in an earthquake.
yeah. And so that's really important to consider. So yeah, I've noticed that because I've lived in both Houston and West Coast. So yeah, you mentioned more concrete here versus bricks.
And that's a lot of homes here now, especially in buildings. There's actually like these earthquake pieces that get attached to your studs.
Oh, that's
And
cool.
So that way it allows for movement.
Yeah, they're like on the floors and stuff. If you don't do it right, they squeak when you walk on them.
Oh, no.
They do, they allow your home to flex without just breaking.
Brackets was the words I was looking for. There's actually brackets that you gotta use over here.
That's cool.
I would say the Carolinas too, a big part of it being brick is the Georgia, Carolina, red clay banks. Because they can make materials there. The other big part is they're settled by the Irish and the English, so it's kind of the habitual building material to build brick banks. But it does do really good. That's what it's doing too.
Yeah, there's also like not a lot of basements in the South, right? I assume is that true in North Carolina as well? Or?
I mean, they're on stilts where I was at, so.
Oh, yeah, so you can't have a
Where to
base.
put your
I
basement.
didn't run across any basements while in North Carolina.
They have a lot more attics, I think, than compared, so like I know a ton of homes here, I've seen more functional basements and attics. I used to build homes here versus over there, they have a lot of functional attics versus, what I've seen over here at least.
Yeah.
That's anecdotal, so don't quote me on it, but.
Okinawa's got tropical stuff hitting right now.
Oh, man. I haven't been paying attention to the tropics too much. All right, let's try to finish up. So blah, blah, blah. So right now we're in hurricane season, of course. And this is just a cute picture of kind of the hurricanes and the intensity. So of course, right, a lot of high intensity in the tropics and anywhere where they can get some steam with wind. Of course, right, we see that over here where the wind brings it up kind of along this path always towards Florida, maybe over here towards like Texas, but sometimes up along the coast as well. And you see, right, not as many, and they usually don't make it past, right, like Baja, California, or anything up here, so they don't make it up the coast. And so we mentioned, right, the eye is that low pressure center, and that's how we get the spiral. So air is always moving towards your low pressure, and again, in our northern hemisphere, that causes our counterclockwise rotation as our Earth kind of moves. And so these are our winds, so we can see how the winds just drive them right along the coast there. And so we already mentioned, right, high winds, rainfall, and of course storm surge, so also why the houses are put on stilts so they can withstand those storm surges. And of course there's been earthquakes throughout time. This 1900 one in Galveston is pretty famous, especially in that area. They still talk about it all the time. Then, anyone experience Katrina or anything? No one. Did you live in Louisiana?
No, in 2005, actually, right after I got over to Camp Lejeune, North Carolina, we went and helped out
Oh.
in New Orleans for 2 weeks.
You know, people that were deployed over there.
Yeah.
that
So
had to go to
what branch were you serving in, or?
Marine Corps.
Dang, that's awesome. What do you have to do, like rescue people or just supply them?
We did a lot of supplies for first aid.
Yeah.
Like just kind of going around helping out different camps and setting things up.
Yeah. Yeah, I mean, that was a pretty devastating one. I was living in Houston at the time, so like where I was living, we were getting a bunch of transplants from Katrina, like joining our school. Yeah.
Andrew, I was away from my little turning 18, go off and travel around with a backpack thing. Everyone's like, oh, you're from Florida, the hurricane. Talked to my parents, and I'm like, oh, you know, we moved up and we're kind of okay. And I was like, all right, well, it was a big one. I came back at the end of the summer to see the effects of Andrew. And we ended up working just a lot of construction and clearing and bits and pieces. But from Florida, lots of hurricanes. I've never seen anything like that. It was just like bombs that hit and he's gone.
Wow. So this was in Florida?
Yeah.
Yeah. Not familiar with Andrew offhand. Yes, I mean, hurricanes can obviously be devastating. There's Ike, Irene, Sandy was another one in recent memory.
So being that we have like certain areas that are prone to these natural disasters and we know it, what kind of prevention is put in place for people that live in these areas that just get hit with these natural storms? Like,
Lower cost of living.
Well, there's also, so,
like, are there buildings reinforced to build like
yeah, so we,
prevent from these type of weather conditions? Like,
yes,
just
so we
just
mentioned,
devastation.
yeah, the bricks, the stilts, but then what happened with Katrina? Why was it so bad? What?
Because it was small, and then when it hit, when it started to break, it got enormous.
Seawater.
But then there was something,
The levees broke. So
Yeah.
it
so
flooded.
these areas, right, so some of them, so the problem with like New Orleans, it is physically below sea level. So then you have all these like dams and levees, right, to keep the water back. So that does kind of protect the people. You know, you have different breaks to prevent the storm surge, so it kind of, you know, breaks up before it hits the coast. So sometimes people do that. But, you know, it's just, there is an engineering limitation, right? People can only predict so much, we can only do so much. So whenever they made the Katrina levees or dams, right, they weren't ever predicting the amount of rain, or they, you know, it wasn't equipped to handle what happened, so then it just broke under the stress.
Like the Carolinas have sandbars that they use
Yeah.
to try to block that rising seawater from coming in.
But
What
like,
does that mean, a sandbar?
Let's see if we can find a picture.
it's so
They build up barriers with sand.
So in the ocean, what they'll do is they'll try to get it to hit something before, so it loses its power once it goes over. So when
It's
it
like
gets to
a-
the shore, it should be much weaker than the initial.
It's like a speed bump. It's like a levee that it's intended to still be allowed to flow over, but slow the volume.
Yeah, so this is kind of
It's a water bottom.
a picture, right, where you would build like an island, something, like a mini breaker out there. There's probably better examples.
Man-made structures.
Potential, yeah, unless there's like a natural feature that you can enhance. So it just kind of depends how it was built.
There's a really good YouTube video that shows some guy, he built a little tank, he put little triangles, like he's an engineer, and he was showing.
Oh, that's cool.
You know, here's a big wave showing it breaking over it, and so it really does a good job at showing like what they try to do, but it's like you can't build something 100 feet tall. I mean, there's just, it prevents it all. It's like,
Yeah.
there's a funny picture, like, oh, we stopped skin cancer, we put a metal plate in front of the sun. You know, it's like, you can't do that. I mean,
Yeah.
you can't build a 150, foot wall above the ocean to hopefully prevent that. It's just not feasible, so there's risks in living there.
Yeah, I mean, and there's risk living anywhere, you know. You can, I think we're pretty good out here. We do have fires, but at least we don't get too many
We're
earthquakes.
running out of trees to burn, so.
I thought we had too many trees. I thought we had to
Well,
burn
did
more.
until we had all the fires start back in.
Oh,
But like, I grew up on the San Andreas Fault, and so we
Yeah.
had earthquakes all the time, so it just became like a normal thing, but, we never, it's like if you were to give Florida, if we swapped for a couple years, they would have no idea what to do with an earthquake, and we'd have no idea what to do with a
yeah, that's also true.
hurricane. Well, I mean, some of us would, but I mean, I could just see the panic. People like, oh, a hurricane in the middle of Medford.
Yeah. Well, actually, I remember too, like with Hurricane Rita, I was trying to finish a chapter, but what caused some of the issues is like people died during the evacuation, so that's always like a question too. Like you don't want to start a panic either. You want to have your evacuation routes ready because people are trying to leave Texas because they said it was going to be super, super bad, and then people ended up like dying on the freeway just because they got stuck there. So, but I mean, and that's also just like it's hard to predict where a hurricane's going to land. You do your best, but okay. Blah blah blah. All right, maybe we'll save this for Thursday. Actually, okay, we should just finish it. We barely have anything left. And we did lab, so, or half of lab, part of lab. So all this graph is just showing, right, kind of our different zones. And so we have our equatorial zone, so obviously that's going to be the hottest in the center here. Then your tropical, right, kind of centered between your Tropic of Cancer and your Tropic of Capricorn. So you have those regions. Then subtropical, again, the continents are in the way, so subtropical. And then temperate now looks, let's see if I can zoom in. So that's like the 40-degree, looks like. Let me see if it's 40. So about 40 south and north, we have temperate, and then subpolar and polar. I think we've kind of gone over that, so just, right, quick recap, equator, weak winds, then we had tropical, strong winds, subtropical, back to high pressure, and weak winds, temperate, strong again, subpolar, we have our summer sea ice, and polar would be lots of sea ice. So let's talk about sea ice formation really quickly. So it starts making those hexagonal patterns, right? So think about molecular structure of water, and then it makes these little pancakes. Then they eventually make what's called these ice flows, just, you know, them kind of smashing together, freezing, coming together over time. And then, of course, don't forget that this water here is kind of going to be losing at the minerals like we talked about, so freezing, right? Your water is frozen, leaving behind most of your minerals and dissolved stuff in solution in your ice water. And so, of course, it does depend on temperature. I think it was like -22 degrees Fahrenheit is where it really starts forming. And then it's kind of self-perpetuating, and of course your ice floats. And you also have circulation of water underneath, right? Warm air rising. But you also have the circulation, so don't forget, right? Ice on top. Then this becomes, right, saltier at the very top here because it's more dense as the ice forms. So now that kind of falls to the bottom, so you get little circulation patterns there as well. And then glaciers. So of course glaciers are larger bodies, and icebergs break off from our glaciers, so floating bodies of ice. We all know it sunk the Titanic too, so you got to be careful. Let's see, lots of, so again, navigational hazards. We mentioned that if we think back, I think the first chapter talking about what led to the potential downfall of the Vikings, it was probably just over time, right? It became more difficult to navigate those polar ice waters. So Antarctica, again, glaciers cover that whole continent, and the edges can kind of break off. We have our shelf ice, and then our shelf ice, of course, would be carried by the currents. And I don't know, people say all sorts of different things with global warming, blah, blah, blah. And so we kind of mentioned, right, winds and wind power densities. So of course, you have to be in an area where you have lots of winds. I know here in Washington, they have a lot of wind power up north. I don't know about Oregon. Are there any wind?
I see a lot of windmills in California, especially on the way to like the Bay, like San Jose area.
It has some out east.
That's what I was wondering.
I've heard it discussed off the Pacific, but.
Yeah, I had a friend that lived in Joshua Tree. I went down to see him. And
Palm Springs and Joshua Tree areas.
Oh, yeah.
Yeah, Riverside, that area.
I wonder what their good metric though. They've been having rolling blackouts and issues with their power grid forever.
I guess that was probably before wind turbines too.
Yeah. Oh, I mean, that's like a whole nother conversation with like our grid's outdated and like probably needs to be upgraded and.
And then off the coast of Maine, they put in wind power turbines.
Yeah, and that's,
In Massachusetts, and it's actually been like affecting, they say like the whales have been dying in that area.
what?
And,
Oh my gosh.
and as well as like the, like oyster, the oysters haven't been coming back like they have for fishermen for quite a while.
Huh.
I was reading it up on that.
That's, yeah, send me those articles. That's interesting. Because some people were saying that like technically maybe they were okay to put in the ocean because they might serve as, you know, marine habitats for things to attach to, but that's kind of interesting what you're saying.
Yeah, I just read some journals on it, and Econ, I was doing a thing about fishing.
Yeah. And obviously, right, we could go into a huge tangent on wind power and like, is it efficient and how does it work? And right, you mentioned battery too, and that's like another big issue is how do we store this power? So even if you can generate wind power, right, let's say it's going, where do you store all that excess energy? And those are questions about our grid too. How do we transfer power? How are all things connected? But I think in the interest of time, we'll stop here. And so it's 11:28. Take a 10-minute break. So we'll convene back at 11:40 for lab, so you get a little break time still. Oh, yeah. Thank you. So if the Sharpies, if you still have some around, I'll gather them. But yeah, we can always talk more during lab about all this. There's so many topics we're touching now.
I have a question for you. I saw on lab 6, there was only one section that needed to be heard like else in person. There was just like videos or not videos.
Yeah, I think it was like going, yeah.
Could I take
Oh, yeah, you could take yours as, yeah, I'm gonna hand them out.
I have
Oh.
especially for veterans, they don't have like any time slots available. So I have an appointment there at noon.
Yeah,
I'm
if
gonna
you
have to
need
miss
it. So you
I-
said,
Yeah, I have a copy. It was just, I think it was activity 3 that I would need photos or something, images.
oh, yeah, I have some photos. You might be able to, let's still look.
Okay, I was just wondering if that's something I could, yeah.
Yeah, you might be able to
take with me
grab
or-